Hello students, today we will discuss about photoelectric effect. In our last video, we discussed about Planck's quantum theory. Okay, right now we will discuss about photoelectric effect. See here, this is a metal surface. Here light falls on the metal surface. When light with a suitable frequency falls on metal surface, then electrons are released from the metal surface. This phenomena is known as photoelectric effect, and the released electrons are known as photoelectrons. See, what is photoelectric effect? When light with a suitable frequency falls on metal surface, electrons are released from metal surface. This phenomena is known as photoelectric effect, and electrons released from metal surface are known as photoelectrons. See, Einstein successfully explains photoelectric phenomena by using Planck's quantum theory. Okay, now come to, this is a metal. Metal is made up of two particles, metal ion and electrons. Metal is made up of metal ions and electrons. These electrons are free to move within the metal, but always these free electrons under the attraction of metal ions. Okay, this is electron, this is metal ion, this is metal ion. Here electron and metal ions are in attraction. These are attractive forces, one type of bonding. These attractive forces are known as metallic bond. Okay, so here electron is bonded to metal ion. Okay, here in order to remove this electron from metal, we need to break these attractions. In order to break these attractions, here some energy is required. So in order to break these attractions, energy is required. That required energy is supplied in the form of light. So this is the light energy. It is supplied to this electron. Okay, now see here electron absorbs energy, light energy. Electron absorbs light energy. According to Planck's quantum theory, absorption of energy always discontinuously takes place in the form of small energy packets, which are called as quanta. Here electron absorbs light energy discontinuously in the form of small energy packets. Those energy packets are called as photons. In case of light, energy packets are known as photons. Okay, that's why here we may assume this light as a stream of energy packets. See here, this is energy packet, this is another energy packet, like this. Okay, see, light, we may assume light as a stream of small energy packets. These energy packets are known as photons. Photon. So here you may consider light as a stream of photons. Here metal surface is shooted with a stream of photons. Then see, each photon is having definite energy. Each photon is associated with a certain amount of energy. See, this one electron receives one photon only. One electron never receives more than one photon. Okay, see here, this electron receives energy from photon and utilizes that energy to break this attraction, these attractions. Okay, now here in case of sodium metal, in order to break this attraction, 2.3 electron volts are required for sodium. In case of sodium, in order to break these attractions, What amount of energy is required? 2.3 electron volts energy is required. Okay, now suppose if we supply energy to this electron, here we are supplying energy to this electron in the form of photon. Here incident photon energy is 2 electron volts. If this photon energy is 2 electron volts, now this 2 electron volts is not enough to break this attraction. Therefore electrons are not at all released out. Therefore there is no photoelectric effect. There is no photoelectric effect. Therefore if incident photon energy is 2 electron volts, then that 2 electron volts is not enough to break this attraction. Therefore electron not released from the surface. Therefore there is no photoelectric effect. Okay, suppose if incident photon energy is 2.3 volts, if incident photon energy is 2.3 volts, then see that 2.3 volts is exactly enough to break these attractions. Therefore these attractions are breaks down. Therefore this electron free from the attraction. Now this free electron coming out and photoelectric effect takes place. Therefore if incident photon energy is 2.3 electron volts, photoelectric effect takes place. Suppose if incident photon energy is 3 electron volts, now this electron utilizes out of 3 electron volts, 2.3 electron volts utilized for the for breaking these attractions. Out of 3 electron volts, 2.3 volts electron volts utilized for breaking this bond. Remaining 0.7 electron volts turns to kinetic energy. By using that kinetic energy, ejected electron move away from the metal surface. Therefore if incident photon energy is 3 electron volts, then photoelectric effect takes place, and moreover kinetic energy and released electron moving with the kinetic energy 0.7 electron volts. Suppose instead of 3 electron volts, 4 electron volts is supplied to this electron. 4 electron volts. Here again 2.3 electron volts utilized for breaking this. Remaining 1.7 electron volts turns to kinetic energy, and released electron move away by using this remaining 1.7 electron volts. Therefore here also photoelectric effect takes place. Moreover kinetic energy will be there. Suppose if incident photon energy is 5 electron volts, out of 5 electron volts, 2.3 electron volts utilized for breaking this bond, and remaining 2.7 electron volts turns to kinetic energy. By using that kinetic energy, released electrons move away from the metal surface. Therefore here also photoelectric effect takes place. Therefore here if you observe this table, with 2 electron volts no photoelectric effect, therefore no electron, no kinetic energy. With 2.3 electron volts photoelectric effect takes place. That supply 2.3 electron volts just enough to break this bond attractions, but no more energy left behind. Therefore kinetic energy 0. In the case of 3 electron volts, 2.3 volts utilized here, remaining 0.7 electron volts turns to kinetic energy. Here when we supplied 4 electron volts, 2.3 utilized for breaking this point, remaining 1.7 electron volts turns to kinetic energy. Here also like that. So therefore here photoelectric effect, here photoelectric, here photo. If incident photon energy is less than 2.3 electron volts, means 2, there is no photoelectric effect. This is the minimum energy required for photoelectric effect. Such minimum energy required for photoelectric effect is known as threshold energy. Threshold energy. Threshold energy. What is threshold energy? Threshold energy is the minimum energy required for photoelectric effect. See here, threshold energy is minimum energy required for photoelectric effect. In case of sodium metal, what is threshold energy? What is threshold energy? 2.3 electron volts. This is the minimum energy required for photoelectric effect. If energy is less than this value, no more photoelectric effect. Okay. So in case of sodium, threshold energy is 2.3 electron volts. This threshold energy is also called as work function. Threshold energy also called as work function. Work function. Work function. This threshold energy or work function is not same for all metals. So metal to metal, this is different. Threshold energy is different for different metals. Threshold energy is different for different metals. Okay. Now this is about threshold energy. Threshold energy is denoted by E naught, otherwise work function means W. Next term, threshold frequency. Threshold frequency, which is denoted by nu naught. Let us come to this equation. E is equal to h nu, Planck's equation. After rearranging this, then you will get nu is equal to E by h. Okay. Suppose here E is equal to E naught. E is equal to E naught. Substitute instead of E naught. Then nu is equal to nu naught. Means nu naught is threshold frequency. Nu naught is a frequency corresponding to threshold energy. What is threshold frequency? Threshold frequency is the frequency corresponding to threshold energy. So threshold frequency is the frequency corresponding to threshold energy. Here threshold frequency and threshold energy are directly proportional to each other. Therefore, what is threshold frequency? Threshold frequency is the frequency corresponding to threshold energy. Threshold energy means this is minimum energy. This is minimum energy required for photoelectric effect. This E naught and nu naught directly proportional to each other. Hence, nu naught is the minimum frequency required for photoelectric effect. Therefore, in other words, threshold frequency is minimum frequency required for photoelectric effect. If frequency is less than nu naught, no photoelectric effect. See here, if frequency is less than nu naught, no photoelectric effect. If frequency is greater than or equal to nu naught, photoelectric effect takes place. No photoelectric effect. If frequency is less than nu naught, no photoelectric effect. If frequency greater than or equal to nu naught, photoelectric effect takes place. Therefore, what is threshold frequency? Threshold frequency is the minimum frequency required for photoelectric effect. E naught is the minimum energy required for photoelectric effect. So, E naught and nu naught directly proportional. This is minimum energy required for photoelectric effect. Hence, this is minimum frequency required for photoelectric effect. Minimum frequency. If frequency is less than that, no photoelectric effect. Okay, nu less than nu naught, photoelectric effect does not take place. If nu greater than or equal to nu naught, photoelectric effect takes place. Now come to threshold wavelength. So here nu is equal to C by lambda. From this, lambda is equal to C by nu. Instead of nu, substitute nu naught. If we substitute nu naught instead of nu, then corresponding wavelength is known as threshold wavelength. What is threshold wavelength? This is the wavelength corresponding to threshold frequency. Threshold wavelength is wavelength corresponding to threshold frequency. Threshold wavelength is the wavelength corresponding to threshold frequency. Here these two are inversely proportional to each other. This is a minimum frequency required for photoelectric effect. Hence this minimum means this should be maximum. Both are inversely proportional to each other. This is minimum frequency required for photoelectric effect. This nu naught is minimum frequency required for photoelectric effect. Hence this is maximum wavelength required for photoelectric effect. Maximum wavelength required for photoelectric effect means if wavelength of incident light is less than lambda naught, less than or equal to lambda naught. See here, if wavelength of incident light is less than or equal to lambda naught, photoelectric effect takes place. Photoelectric effect takes place. If incident light wavelength is greater than lambda naught, no photoelectric effect, no photoelectric effect. Therefore, what is threshold wavelength? It is maximum wavelength required for photoelectric effect. If wavelength is more than threshold wavelength, no photoelectric effect. Okay. So these are the three important terms: threshold energy E naught, threshold frequency nu naught, threshold wavelength lambda naught. Threshold wavelength lambda naught. Okay, now come to see here this. If energy of incident photon is less than E naught, like this. Here E naught is 2.3 volts. Here suppose the incident photon energy is 2.0 electron volts. Here this is less than that of E naught. Therefore no photoelectric effect. Therefore if E less than E naught, no photoelectric effect. Okay. E and energy and frequency directly proportional. That's why instead of E, nu. Instead of E naught, nu naught. If nu less than nu naught, no photoelectric effect. Okay. E greater than E naught, like this. These are the energies of incident photons. These are more than E naught. This if energy of incident photon is more than E naught, then photoelectric effect takes place. Therefore, if E greater than E naught, otherwise nu greater than nu naught, photoelectric effect takes place. Moreover, there will be definite kinetic energy. If E is equal to E naught or nu is equal to nu naught, photoelectric effect takes place, but kinetic energy 0, like this. So here energy, in case of threshold energy supplied is exactly enough to break these attractions. No more energy left behind to turn to kinetic energy. That's why if E is equal to E naught, photoelectric effect takes place without kinetic energy. Okay. Now come to photoelectric effect equation. Photoelectric effect equation. Suppose see here energy supplied to this electron in the form of photon utilized for the purpose of breaking off these attractions. This is one. And if any energy remaining, that remaining energy turns to kinetic energy. Therefore, energy supplied to the electron in the form of photon, energy of incident photon is equals to threshold energy which is required to break the attractions between electron and metal ion, plus remaining energy turns to kinetic energy. Therefore, as per law of conservation of energy of incident photon should be equals to threshold energy plus kinetic energy of photoelectron. Here energy of incident photon is denoted by E, threshold energy E naught, kinetic energy of photoelectron Ke. Therefore, E is equal to E naught plus Ke. So from this Ke is equal to E minus E naught. Ke is equal to E minus E naught. So E is equal to h nu, we know E is equal to h nu. Instead of E, substitute h nu. Instead of E naught, see here, from this E naught is equal to h nu naught, substitute. After taking h common, then this equation becomes Ke is equal to h into nu minus nu naught. This is important conclusion. Next, we know nu is equal to C by lambda. Instead of nu, substitute C by lambda. Instead of nu naught, you may write nu naught is equal to c by lambda naught. Mu naught is equal to c by lambda naught. Then you will get Ke is equal to h into c by lambda minus c by lambda naught. Remove c common, therefore Sc is equal to 1 by lambda minus 1 by lambda naught. Therefore Ke is equal to Hc into 1 by lambda minus 1 by lambda naught. So this is the, therefore final conclusion, kinetic energy is equal to half mv square. Kinetic energy of photoelectron is equal to half mv square, which is equals to h into, in terms of frequency, h into nu minus nu naught, in terms of wavelength, Sc into 1 by lambda minus lambda naught. This is very important equation.